Going to be an exciting session. I'm very excited to be talking about innovation, how it's going to take us to the extremes of our universe maybe, and how NIAC, which is NASA Innovative Advanced Concepts, is playing a role in that endeavor. And hopefully you can as well. So this presentation is going to be interesting. We're going to start off with some boring business material, perhaps, but it's an opportunity for you guys to maybe be involved in NIAC. So I want to introduce the program to you. And then we'll have three panelists who will talk about extreme environments and some of the technologies that will enable us to explore them. So NASA Innovative Advanced Concepts. It's a small program. These are the program officers. Jason Derleth is the program executive. He sits at headquarters. I'm the program manager. I look a little young for my age, but I streaked my hair, tried to pepper it, making me look older for this occasion. We have Ron Turner, Kathy Riley, both of whom have been with NIAC for very long, since the 90s, and Barb Mader, who's our budget analyst. So NIAC is one program that exists in the Space Technology Mission Directorate at NASA. There are 9 programs in that mission directorate, and NIAC falls in the middle category. It's one program that looks at pioneering new ideas and implementing new technologies that are early stage. They are low on the technology readiness level scale, TRL if you know that term. And NIAC is interesting because it doesn't look at just one specific technology effort. We try to encompass a broad range of scientific disciplines. So anyone who's interested in proposing to NIAC from science or engineering or operations can certainly do so. And we also encompass a wide range of institutions as well. So universities can be involved, national labs, government, industry, garage inventors, and individuals as well. So we're very open from that standpoint. What does NIAC fund? Well, we have a lot of interesting ideas that we have invested in, and I just want to give you a flavor of those that we've previously funded in the past year. And then, of course, our panelists will talk about their efforts as well, and they'll go into more detail. So one idea we have recently is, came out of Virginia Tech, and he's looking at building a heat shield from tensegrity structures, and once that heat shield lands on Mars, it converts to a mobile rover. We have another concept coming out of nanomics. They're looking at stellar echoes from a distant exoplanet. So they're looking at solar intensity fluctuations. You know, a distant star has a solar flare, and those signals bounce off structures, planetary structures, and may perhaps give you continent-level imaging resolution. This idea is very NIAC-y. We're launching, so these guys from Made in Space, they're launching a 3D printer onto an asteroid, converting that asteroid into an autonomous spacecraft, and then infecting other asteroids. This next concept comes out of Princeton Satellite Systems. They're looking at a fusion engine to explore Pluto. Not only fly by like New Horizons did, but orbit it and land for science. This next concept here is a thin film spacecraft that proposes to wrap around space debris and deorbit them. And this last one comes out of Ames. She's looking at reprogramming microorganisms to recycle electronics. So eat them up, crunch them up, and then print them out into more usable circuits. So that gives you a flavor of the kind of ideas we fund, and hopefully something there attracted your interest and makes you want to propose as well. So if you do want to propose, here's some key information. We have 2 phases of study that we fund. There's a phase 1 for up to 9 months of study at $125K. And then there's a phase 2. Once you submit that final report for the phase 1, you're eligible for phase 2 at $500,000 and 2 years of further development. So we fund visionary concepts that address our nation's goals, and we will be looking for proposals that offer radically different approaches ones that offer new mission opportunities or offers magnitudes, orders of magnitudes improvement on existing technologies. So whatever you propose, though, needs to be placed in a mission context, which means we don't fund just widget development. If you have a cool toy, cool technology, you need to put it in a mission context. How can it be used to do some specific science or explore some specific endeavor? So you can learn more about our solicitation on our website as well, but we do have 4 important evaluation criteria that you kind of have to adhere to as well. So the phase 1, which is your kind of gateway into NIAC, consists of 2 steps. We have a step A and a step B. The step A is really easy. It's a 3-page white paper. Really easy to do. And that will allow us to essentially evaluate your concept before you invest too much time and let you know whether or not you're compliant within NIAC. And if you're compliant, usually you'll get invited to a step B. And that's just only an 8-page proposal as well. And once we get those in, those go into panels for review. OK, so there are things that we don't fund. And there are 10 of them that we've traditionally not funded in the past. So I'll just quickly go over them. You'll be deemed non-compliant if you have no aerospace focus. If your concept's unclear, if we have no clue what you're doing. If you're not programmatically credible, so if it takes 3 times the world's GDP to do, we won't fund that. If it's a tool or process, for instance, you want to create a model-based system, and that's the sole endeavor of your project, then that's not good. If you want to create a model-based system that enhances your ability to study something, we can fund that, but not exclusively. If it's not technically credible, like you want to do warp drive, but you don't know how. If you want to do just solely experiment or research, without that mission analysis, we won't fund that either. So we don't fund just a lab experiment. If it's been previously studied, we won't fund it. If it's been previously studied, but you're offering a new alternative way to do it, or there's new technology that enables it, then we'll look into that as possibly fundable. If your technology development is narrowly focused, so maybe you're focusing on a specific subsystem without looking at that mission architecture, we won't fund it. If your idea is incremental, then if you can achieve it in 5 years, that's not worth our time to fund either. We want to fund things that are very far out. There are other programs in NASA that does fund nearer-term technologies, but that's not the goal of NIAC. If your mission application is unclear, so you do have a mission context, but we don't really know how that applies, we won't fund it. So here are some key dates. We're releasing our next phase 1 call in October, and you'll have several weeks to submit that phase of the step A proposal. We'll offer a virtual forum, which gives you the chance to ask questions about our solicitation as well. And then these are some target key due dates as well. And your only deliverable are a couple of reports and attendance at meetings. So they're really fun meetings, actually. One's an orientation meeting. It's kind of like this, Mile High Club or something of really smart guys and girls. And then there's also, we have our own symposium as well for our fellows, but everyone else is also invited. It's an open forum for exchanging ideas. And then, of course, we all want more money, so the phase 2 is what you want to eventually target. You've got that phase 1. You've turned in your final report, and so you're eligible for that phase 2, again, at $500,000. So as I mentioned before, the phase 2 is going to look at studying your detail in greater depth, and that's really the goal of the phase 2 for the most promising concepts. So I leave kind of with this beautiful art rendition. One of our early fellows, Anthony Longman, he studied a space station architecture. And he had an artist kind of paint this vision for what his space station looked like. It's pretty radical, right? With mountains and valleys and streams. So yeah, the future depends on you. I'll take questions about NIAC before we jump into our panelists here, if anyone has them. Oh, actually, there may be live stream questions. So this means everyone's going to propose, right? Yeah, even students can propose, okay? Yes, please.
Maybe I read it wrong, but I think your chart said release target in August. I think you said October.
I apologize. We will probably be releasing in August. That's correct on the slide. That's all subject to fluctuate, of course. Yeah, you're welcome. Thanks for catching that. Okay, so everyone's good to. Oh, okay, another question.
Is there a chance you'll post these slides on your website link in the NASA domain?
We'll look into that. I think there is some version of this already online, I think in PDF format from last time. So we'll look into posting as well. Thank you. Okay, again, so there's about, what, 200 or 300 of you here. Expect 200 or 300 proposals next fall. Okay, I'm going to introduce you guys to our next panelist, our first panelist member. And how this is going to work is our panelists are going to talk about, again, their extreme environments, and then we're going to go into another question and answer session. You can ask them about those environments themselves, and then they're going to come back up and talk about technologies that enable that environment, and then we'll have another question and answer session. So our 3 extreme environments are Interstellar, Venus, really hot, and then Icy Moons, really cold. Okay, so our first speaker, Mason Peck, is an engineering professor at Cornell University. He also served as NASA's chief technologist from late 2011 to early 2014. His research interests include spacecraft dynamics and control, mission design, and technology development. Mason led and participated in NIAC studies, including a NIAC Phase 1 study on superconductivity, whose technology has matured to be one of the approaches now being considered by JPL and their Mars sample capture and Earth return. He also did a NIAC study Phase 1 on using centimeter-sized spacecraft for exploring asteroids and Europa, for which the chipsat technology was demonstrated on a Kickstarter-funded satellite. A NIAC Phase 1 study also on an energy scavenging underwater rover for exploring Europa, and a NIAC Phase 1 and Phase 2 study on electrostatically charged using electrostatically charged on a spacecraft to warp its orbit within a planetary magnetic field. So he's done a lot for NIAC, basically. Please welcome Mason Peck.
Well, thanks very much. I just have to comment that, so I work at Cornell University, I'm an academic, and NIAC was the very first research award I ever received as an academic. As a faculty member starting out, I think what it did was sort of ruin me for anything else. It honestly taught me that you can reach pretty far and think freely, and there's at least some source that might find your ideas appealing. So I want to thank NASA and NIAC in particular for encouraging me to think a little outside the box, and I've been trying to do that ever since. Do we have the slides for my part of the talk?
It's, there's a pointer right
I'll just play it, okay. And questions? All right, so the extreme environment I'll talk about is the interstellar environment. And I know we're in a post-fact society, but I did bring some facts with me. I'm a little behind the times, I guess, but I'll do what I can. This picture is meant to suggest the appearance of a black hole. It kind of reminds you of the movie Interstellar. And this actually comes from some work by Oliver and, oops, can't see his other, can't quite read that, but there. Anyway, there's a citation. If you're particularly curious, you can find the software and plot your own interstellar space. So the thing is, why would you do this? Why would we even contemplate interstellar flight? You know, after all, it's very hard even to get to the outer solar system these days. In fact, frankly, it's even hard to get to low Earth orbit. So why are we even thinking about interstellar space? I would offer that it's because it's one of those things we should be thinking about. If anywhere in the government is going to be thinking about something like interstellar space, it'll be NASA, and specifically, it'll be NIAC. So I think it's the right answer that someone should be looking at this. One of the reasons, though, practically speaking, is there's new science to be done. We have this great process in which scientists use a decadal survey approach to every now and then figure out what are the high priorities for space science, for heliophysics, astrophysics, planetary science, earth science. That approach works great. We're able to identify some high priority activities, but every now and then new information comes along. Kepler has identified, some 6,000 planet candidates. A number of them live in the so-called Goldilocks zone, the place where we could, in fact, see something Earth-like. And kind of amazingly, one of those is the closest possible star to us, Proxima Centauri. So this planet, which we call Proxima b, lives in a little region fairly close to this weak star, where it gets about the right temperature, potentially, to be Earth-like. It's a rocky planet. It's not one of the large Jupiters or something where clearly something like Earth life couldn't exist. So, why do this? Well, I think if you're going to study Proxima b, study another planet that we've never seen before, you got to at least cross that chasm of 4.24 light years to get there. So it's worth talking about these things. Another good reason, and I should hurry up and say this before Jeff Landis gets here because he knows way more about it than I do, but here's an idea. Remember that mass bends space-time, right? So if you move far enough away from our sun, which is a massive object, the light traveling from behind the sun and then around the periphery of the sun gets focused at a point which is roughly 550 AU away from the sun. In fact, it extends out quite a bit from there. So there have been a number of ideas about how to do this lately, and Jeff's been working on this particular issue. But even if you're not going all the way to Proxima b, what about everything in between? This is one of those great ideas. Gravitational lensing. If you were to get a spacecraft to this 550 to maybe 2,000 AU point away from the Earth, if you could do that, you might be able to image the surface of an extrasolar planet down to about a 1 kilometer resolution on its surface. That'd be incredible. That would be obviously game-changing. But there's no hope of doing that with today's technology. But the technology you might develop going to something like Proxima b or Alpha Centauri, that could get you there in about 2 weeks, or even nearer to home. You could reach the heliopause in about 3 days, maybe Mars in an hour, the moon in 6 seconds. All these things have a lot of implications for not just the extraordinary science that might happen at a place like Proxima b, but also some very near-term practical applications. It might help us do something economically viable for the moon or for Mars. It might help resupply, let's say, a Mars colony. So there's lots of reasons to be pursuing this beyond only interplanetary science or interstellar science. Another reason may be because it's there. This is George Mallory. He came to a sticky end, but some people climb Everest, some people go to space, some people reach very far because that's what we do. It's one of these fundamental human things. It's not just about making money, it's not just about achieving some scientific renown, it's because it's the first time it's been done, and that's the kind of thing we do. Now let's talk about the environment and why this is hard. This is a weird plot. Don't know if I've ever seen anything like this before, but I'm going to try to talk to it. You can barely see on the lower, on that horizontal axis, that is distance from the sun. It's in log of space, though. Okay, so let's see if I can make this work. All right, so this is log of distance from the sun. We start right in the middle of our sun, and then moving away, yes, I know the sun is circular, but in a log space it looks like that. Moving away from that, we cross the orbits of Mars, Venus, Earth, not in that order, Mercury, Venus, Earth, and Mars, and then we get to the asteroid belt, which compresses to something like that. We have the planets, the outer planets from there, which are that high, but in log space they're very, very thin. You could imagine yourself traveling at a maybe constant speed on this log plot, which is, say, accelerating all the way through all this stuff, and this is kind of what you would see. A little gap here of 20 years, and then you catch up again with this other solar system, the Proxima Centauri solar system. Oops, sorry, I need to go back one. There we go. And in this location, 21 years later, you finally see the same kind of solar flux you saw back there 20 years ago or 21 years ago around Earth orbit. So you spend about 21 years with essentially no solar power, which means almost without any heat. And you guys know how hot it is out there in interstellar space, right? All you get is the background radiation from the Big Bang, a little less than 3 degrees Kelvin, or 3 kelvins. So there's not much energy available out there. In fact, there's so little available that all the resources you probably are going to want to accelerate out that far are only available right around here. After this point, you haven't got a lot of options. Solar sails, fusion, these are all potential ideas. The only idea that I've seen that seems to work is the one that's been called Breakthrough Starshot. So maybe some of you are familiar with this. This is an idea that's sponsored by Yuri Milner. He's a billionaire in San Francisco. The notion is you'd like to build something very small to accelerate because, after all, energy is expensive. And if you can accelerate it quickly enough, you might be able to reach a fast enough speed close to the Earth that you can continue to use Earth resources, even though it's only going to coast for the next 20, 21 years, all the way to Alpha Centauri. So I have a spacecraft in my pocket. This is a prototype built by Hunter Adams at Cornell University. Zach Manchester innovated a lot of this stuff. In fact, Zach was responsible for building the KickSat-1 spacecraft, which took about 100 of these things to orbit a few years ago. So this little spacecraft has solar cells, has communications, it has processing, all that sort of thing. It's virtually every subsystem you would want on a spacecraft. This, and then Phil Lubin's NIAC work from 2015 on accelerating a sail with a laser, came together in the form of this Breakthrough Starshot project. So if we could accelerate something that's a gram-scale spacecraft using, let's say, lasers to impart enough photon pressure to that thing, then maybe we could get there as fast as a human lifetime. And that's kind of important to us, right? We'd like to see these things happen. We might also be excited for our grandchildren or our 10 times great-grandchildren to also see them, but I'm less patient than that. So I would like to see this happen soon enough that I could appreciate the results. That's the idea. So can you send something through this really hostile environment and have it reach somewhere interesting in a human time frame? So that's why this is hard. There's no resources. It's going to take a long time. Maybe the time is doable, but then the real problem here is the interstellar medium. That's the hostility we encounter from here to there. So let me talk just briefly about the Breakthrough Starshot concept, just so you have some idea. I'm not really advocating this here. I'm giving you as an example of one way in which you could try to get around some of the environmental issues in the interstellar medium. So there's this dead zone I described, where from pretty much 1 AU near Earth to about 1 AU near the destination, you've got nothing. There's nothing to depend on, nothing you can get. Yes, there are some other concepts. There's a concept where you have a big scoop that scoops in some interstellar material and performs fusion on that. There's 4 or 5 miracles required for that to happen. There's only like 2 miracles for this to happen. So I'm going to go with the fewer miracles and talk about this example instead. So the idea is you have this large optical array on the ground that puts about 50 gigawatts of laser power toward this very small, thin sail, accelerating it at about 60,000 times Earth's gravity for about 2 minutes. Even though it goes very fast, it stays relatively close to the Earth during that time, so it's not impossible, it appears, to focus the light for that amount of time. There's some very subtle dynamics and control issues. There are material science issues. For example, how do you make something like this that doesn't just burst into flame and disappear when you shoot it with that kind of power? Yeah, there's a few problems. Nevertheless, it's at least conceivable on a, let's say, 20-year time frame that we may be able to mature these technologies to where they want to go. So I'll talk more about that later on, but just to give you some sense, that's why we're looking at this particular problem. The other thing that I think no one has talked about yet, and which I hesitated even to put up here because I think it's a brilliant academic problem, is how do you navigate in the presence of relativity? As an example, it takes something like 21 years for this object to get to Alpha Centauri or Proxima Centauri, about the same distance. You know, what's 0.1 light years, give or take. The proper time as measured on this spacecraft is about 20 and a half years. So you lose about 6 months. This thing is 6 months younger when it gets to its destination than an analogous spacecraft that stays in Earth orbit for that entire time. And what that means is that if you were basing the navigation on an onboard clock, given that you probably can't communicate with this thing maybe at all, on the trip, you're going to be wrong by about 6 months in the time that it take to arrive. And yeah, you'd anticipate that, but if you weren't anticipating it, we're talking about hundreds of AU, maybe thousands of AU worth of deflection away from where you want to be. Some other cool stuff that happens. We'll talk about the technology a little bit later. Another few things that happen have to do with the interstellar medium. So let's talk about that a little bit more. So in the interstellar medium, there's stuff between here and there, not much, but a little bit. Let's say for this 21-year mission to Alpha Centauri, you would encounter about 10 to the 6th, about 1 million impacts of something per square centimeter. So 1 million impacts per square millimeter of something. Those some things are little particles. Maybe they are ions, even electrons, but some are kind of large objects. You'll get something like 600,000 impacts with 100 nanometer particles. Now you're probably thinking, that's no big deal. I can shield that. I'll put a few millimeters of aluminum, everyone's fine, right? Yeah, that might work going, 0.2 C, but I guarantee any particle striking a surface at a significant fraction of the speed of light it's going to be a bad day. So I think rather than trying to shield this, what you would do is let it happen. Embrace the impacts, and just let them drill right through the sail or the electronics. Now, how do you make electronics that can stand having holes drilled in it at 0.2 C millions of times over? I think you have to have an entirely different approach to electronics. I think you don't have nanoscale circuitry. I think you probably have to blow this up. So we have to have, let's say, a 4 meter square sail. You might print these electronics so that the individual traces are millimeter scale. And with that size, you probably can statistically survive a number of these impacts. Now, maybe they won't all survive, but one of the architectures here of interest is make enough of these little chipsats, or sails, that you launch one a day for several years. I'd be glad with 1 or 2 bits from Alpha Centauri, but maybe more of them will survive than that. So if even only 1 out of 1,000 make it, I think that's still a good result. A few things about the interstellar medium beyond just there's particles in the way. Another one is the plasma interaction. So this is some really weird stuff. Turns out there's plasma between here and there. It's actually about 7,500 Kelvin, which sounds really hot, but there's such a small amount of it that the thermal energy doesn't really count for much. So really, it's that Big Bang temperature that you have to encounter. So it's super cold. As the plasma particles drill through the sail, which they will do, or maybe a few of them bounce off, you can't really treat these particles, even the macroscopic ones, as if they're cohering the way matter normally would. It's almost like just a cloud of electrons and ions and stuff. So in fact, what happens is, according to Bruce Drain from Princeton, where I took most of this information from, what happens is the ions probably pass right through the sail, and the electrons probably stay behind. The result is you end up with an electrically charged surface. Now, my 2006 or 7 NIAC award was actually talking about exactly this. What happens when electrostatic charge can cause a spacecraft to deflect in a magnetic field? And there is interstellar magnetic field. It's something like 3 microgauss. It's very small. Okay, but remember, this thing is traveling at near the speed of light. So if you remember the Lorentz force, this is charge times velocity across the magnetic field. Velocity and magnetic field here are almost perpendicular, it turns out. It's just the direction of the magnetic field. So you're going to get a significant Lorentz force. That force is enough to deflect the path of this guy between maybe 1 and 100 AU. So if you don't get this right, you've missed your planet by about 100 times the size of its orbit away from the sun. These are the kind of no-joke problems that arise when you're talking about navigating in interstellar space. If you're a golfer, what you have to do is kind of slice this intentionally and have it kind of curve its way into the planet. A couple other quick things. I talked about the proper time, the fact that relativity is important here. Another curious thing that happens is as the interstellar medium strikes our spacecraft, it heats up. So there is some thermal energy that arises there. It's maybe not a lot, maybe 80 kelvins. It still might be enough for you to extract that energy thermally through some Seebeck effect or something. I kind of doubt it. It's not much, but still it's something. Ideally, what you do is put your spacecraft to sleep for about 20 years and have it wake up when it's finally got enough power to do something. What that means is that the trajectory's got to be entirely passive. You just kind of shoot and dead reckon your way toward the destination. So this is a hard problem, and I think we don't know how to solve it yet. But thanks to NIAC and thanks to some of the energy bidding put into this by the Breakthrough Starshot folks, we're at least knocking down some of the hard problems associated with this. I'll be glad to talk more about that, but later on in the day. So thanks.
Thank you, Mason. I guess the world is not enough. Our solar system's not enough, but our next speaker, he's going to bring it back closer to home, relatively. Dr. Jonathan Saude is a mechatronics engineer at the Jet Propulsion Laboratory in the Technology and Fusion Group, which seeks to bridge the TRL Valley of Death for innovative, promising technology concepts. Jonathan focuses on developing unique and innovative mechanical systems, many of which are related to deployable antennas and sunshades by taking concepts from ideation to verification by testing. He's also currently the mechanical engineering lead on the RainCube spacecraft. Jonathan is leading the NIAC study, Automaton Rover for Extreme Environments, which explores how to enable a long-duration Venus rover using mechanical technology. Please welcome Jonathan.
Thanks. And I should note, it's a huge honor to be here, and thank you for the introduction, Alvin, to be on this panel, especially with both Mason and Jeff, who are multiple times NIAC winners. This is my first time in the NIAC program. I'm pretty fresh to this. But what we're looking at right now is Venus. And Venus is a really fascinating planet. With a temperature that'll melt lead, a pressure that'll crush the hull of a nuclear submarine, and a sulfuric acid atmosphere, it's probably one of the most extreme terrestrial environments we would want to try and send a lander to. Now, just to give you some context of what that means, if we look at Earth that has an average surface temperature of 22 Celsius, Venus has an average surface temperature of 462 Celsius. And if you look at some of the technologies we have developed, mil-spec electronics, some of our most robust commercial off-the-shelf electronics, only operate up to 125 C. Solder and lead melt at 300 C. And I should note, paper spontaneously combusts in between these two temperatures. So there's a lot of limitations if you want to put something on the surface of Venus that's going to survive and operate. To give you an idea of what the pressure is like there, if you took a gallon of air here on Earth, it would compress to just 1.5 shot glasses on Venus. That means you have advanced corrosion rates, and you have to be very careful with anything that would be a pressurized system. Despite this, we, as a human species, specifically the Soviet Space Agency and also NASA with the Pioneer probes, have landed about a little over half dozen probes on the surface of Venus. This is an image taken from one of the Soviet Venera landers. But the longest that we've been able to have an object survive on the surface of Venus is 2 hours, 124 minutes before it succumbs to the environment. The challenge is that the electronics just can't take the heat. They stop operating once the temperature gets too high. And this is one of the key challenges that this NIAC addresses, because in order to understand more about Venus, we need to be able to be on the surface of Venus for a longer period of time. And I think to really do good science, we can really get at some new science goals if we can rove the surface of Venus, drive around Venus, start sampling different geological units in just an individual location. By being on the surface of Venus for a period of months, we can look at time-dependent behavior, things like the sulfur cycle on Venus, understanding what Venus weather is like. And you may be wondering, that's great if you're a Venus scientist, but why should we care? Why should I care? And actually, there's a good reason that everyone should care. As Mason had mentioned earlier, it's really one of the things we're finding out recently is that there are potentially billions of Earth-like planets in the habitable zone out there across the billions of stars in the galaxy. And we're looking at and developing various ways to image those exoplanets now. But as we start looking at these exoplanets, we're wondering, which one is an Earth 2.0? Which one could possibly support life, or which one could we someday see about going to one day, our great-great-great-grandchildren? And to help understand and know what are the planets of interest, we can, of course, look at Earth. And we know where Earth is at in proximity to the sun. And we've done a lot of exploration on Earth. Granted, there's a lot of mysteries that we still don't know, but we're constantly knowing, and getting a better idea every day what makes Earth the planet that it is. But we're very fortunate, actually, to be in a solar system that has 3 Earth-sized terrestrial planets that are in or near the habitable zone, Mars and Venus. Now, we've launched a lot of missions to Mars, so we're constantly learning more and more about how Mars formed and what made Mars the planet that it is. But Venus is a real mystery. It has a thick sulfuric acid clouds around it that makes it very hard to understand what's going on the surface of the planet. And if we can get some long-duration landers and rovers to the surface of Venus, it can help us understand what makes Venus the way it is, what formed it the way it is, so that when we look out at those exoplanets around other stars, that maybe it can help give us clues to know, are we looking at an Earth, Mars, or Venus, and which ones may we want to go to. So that's the challenging portion of it, and I'll get into the technology for how we do put a long-term rover on the surface of Venus later.
Thank you, Jonathan. I hope you guys are paying attention, because after our next panelist speaks, I'm going to ask you to vote on who convinced you is the most extreme environment there is. So, Jeff Landis is a researcher at NASA Glenn Research Center. He was a fellow of the original NIAC Institute for Advanced Concepts in 1999, where his investigation of small laser push light sails first proposed the concepts that are being developed in the Breakthrough Starshot project to send a probe to Alpha Centauri. He's also a fellow of the NASA Innovative Advanced Concepts Program now, where he is working on concepts for exploring Venus, or he has worked on concepts for exploring Venus, Triton, and Titan. He is an associate fellow of the AIAA and a recipient of the AIAA Aerospace Power Award for contributions to power systems for planetary and space missions, and the AIAA Abe Zarim Award for faculty advisor for mentoring student researchers as a faculty member of the Aeronautics and Astronautics Department at MIT. In his spare time, he is a Hugo and Nobel Award-winning science fiction writer. Please welcome Jeff.
Thank you. Thank you. Let's see. Does this work? So let's talk about some places in the outer solar system. We talked about Venus close into the sun. We talked about interstellar flight going away from the sun. But there's places in the solar system between that are actually some very fascinating places. Let's talk about this planet, Triton. I say planet. It's the size of Pluto. It was visited once. This is the retrograde moon of Neptune. It was visited by Voyager, one of the least known places in the solar system. There's a whole disk color image of Triton viewed from Voyager. Well, what is it about Triton? Well, it's a big moon, 1,500 kilometers across, bigger than Pluto. It's in a retrograde orbit. That's very odd. It's the only large moon in a retrograde orbit. So there's that retrograde orbit. That typically indicates a captured body. It also indicates that it's not going to be there forever. If it's a retrograde orbit, tidal forces will eventually bring it down. And the last thing about it is it's pink. That's the whole color image. So that's not merely a moon. That's a captured Kuiper belt object. There's the relative size. There's Pluto. There's Triton. So Triton is, in fact, Pluto's twin brother. So there's a photo mosaic of images from Neptune, kind of interesting territory. It has that, what we call cantaloupe terrain. up in the north half, sort of the top viewed from there, and it has that pink material on the bottom side. Well, it has some other problems, one of which is it's pretty cold. But despite that, it has an atmosphere. Now that we've seen that Pluto also has an atmosphere, that's a little bit less surprising. It's a very thin atmosphere. It's 1.4 to 1.9 Pascal. You're all aeronautical scientists, so you know what the Earth's atmosphere is, right? Everybody knows that? Right, 101.325 Pascal. So this is a little bit over 1/100,000th of the thickness of the Earth's atmosphere, but it's still there. Nitrogen, traces of methane, and it has these sort of interesting features on the surface. Take a look at that little feature there. I want to get a little bit closer. Oh, come on, move forward. That seems to be a wind plume. Triton has geysers on the surface. Here's a view from Michael Carroll, one of my favorite space artists, sort of the best view of the surface of Triton. And it has these liquid nitrogen geysers that bring up material from deep inside out to the surface of Triton. That's a surface that's about 33 to 35 degrees Kelvin, by the way. So when you go there, make sure to bring your thermal underwear. But nevertheless, a very fascinating place. It has one side constantly facing the planet Neptune, visible off in the distance. So why? What's exciting about Triton? Well, it's the largest and closest of the Kuiper Belt objects, because it clearly is a captured Kuiper Belt object, like Pluto. Pluto is exciting. Triton is bigger. It's even more dynamic. It's a whole class of worlds in our solar system, which we're only beginning to learn about. That pink color, I mentioned the pink color. That pink color is a material called Phtholons. These are complicated long-chain polymer organic compounds. They're characteristic of Kuiper Belt objects. Most of the Kuiper Belt objects, well, many of them are pink. That's pink because of the Phtholons. These are probably the compounds from which life was originally put together. These are the primordial organic compounds in the solar system. And because of the presence of Neptune, turns out to be the easiest of the Kuiper Belt objects to reach. It's interesting in and of itself. It has that cantaloupe terrain. It has geysers. It has winds. It has many interesting science targets. What's on the surface? Well, mostly nitrogen, ice, and snow, plus some amount of carbon monoxide, carbon dioxide, methane. Well, that was one of the interesting moons in the solar system, but let's think of another interesting moon in the outer solar system, an even bigger one, Titan. In fact, named Titan because it's so big. This picture of Titan and Saturn is a little bit misleading. Titan is not actually almost as big as Saturn. In this photo montage, it has to be a lot closer to the viewer than Saturn is. Still, it's pretty big. But it's amazing. Here's a view of it. That's haze in the atmosphere of Titan. So I say, wait a second. Titan doesn't merely have a 1 to 2 Pascal atmosphere. It has an atmosphere that's actually denser than the Earth's atmosphere. In fact, it has more total atmosphere than the Earth does. But it has stranger things. Here's a view kind of with Titan almost at crescent Titan. We're looking almost at the sun. And there's a glint on the surface. What the heck is that glint on the surface? Well, we can never see the surface of Titan with visible light. It's opaque. It's opaque because of those Phtholons in the atmosphere. You can think of it as the planet of photochemical smog, if you like. But we can look through that atmosphere with radar. And here's a radar imaging of Titan. And radar imaging, of course, is done in colors that you can't see because your eyes are not sensitive to radio waves. But the people who put the false color in this image colored the very flat areas blue. And that's indicative, in fact. It's indicative because they are liquid. Titan is the only place in the solar system other than Earth that has liquid on the surface. Not going to, oops, that was my last slide. Let me go back. Other than Earth, it's the only place with liquid on the surface. But because of the low temperature of Titan, Titan's a temperature where water is a synonym for rock. The rocks on Titan are made out of water ice. So those liquid surfaces that we see, the lakes, the small seas on Titan, those aren't water. Those are, in fact, hydrocarbons. Those are ethane and methane. So Titan, interestingly enough, is a planet that has hydrocarbon lakes that, in fact, has more hydrocarbons than all of the fossil fuels on the planet Earth. So if you're talking about looking for fossil fuels and solving the energy crisis, hey, I have a place to go to that has all of the hydrocarbons that you need. Only problem is it's a little more than 1 billion kilometers away. Take it away, Mason.
Thank you, Jeff, and the rest of the panelists for these extreme environments. Before we start on some questions, I just kind of want a show of hands of whether you think Alpha Centauri or Interstellar is the most extreme environment. You know, you're gonna, anyone? Okay, Venus, anyone? Okay, Icy Moons? You gotta vote for your own one, Jeff, you know? Oh, no one's voting for yours, Jeff. Look at this. Okay, there you go. Okay, so I don't know if we can move this back for questions. I don't know if everyone can see them, but that's okay. Okay, I'll just ask some questions then. So Mason, besides going to Alpha Centauri, are there other promising targets interstellar? If you could go anywhere in the galaxy you wanted, where would you go?
Well, I mean, I think the great news here is that Kepler has identified so many planet candidates that we really have our pick if we're not limited by the technology to get us there. And by the way, it's not just propulsion technology, it's also communications technology. You know, how do you actually send data back from even a large spacecraft, but more likely a very small one? So in terms of other targets, I think one of the reasons I have always found space exploration appealing is I have some notion that maybe someday I could go there and check it out. Maybe if I make it to retirement, I could retire to a nice place in Valles Marineris on Mars, or, you know, Elon Musk will have the expensive house up on the hill. I'll have a little suburb thing, but nevertheless, that would be appealing, the prospect of actually going somewhere. I think you could actually, not you, not me, at some point, someone might be able to go to a place like Proxima b. Those locations that are, you know, on the order of tens of light years away, maybe 100 light years away, even though we know that there's something out there, I just don't see with any physics we understand today how anybody would ever get there. So I guess I'm more interested in those places that are in fact within reach.
Very cool. Oh, someday I hope to go there as well.
Give it a try.
So Jonathan, we have this question from online. There has been discussion on a floating habitat on Venus. You know, how viable is this, and how does that maybe fit into your understanding of?
That's a great question, and actually, the first NIAC proposal I wrote was around a floating habitat for Venus, actually. It was not selected due to some technical issues with the idea, but I think a floating habitat on Venus is a really good idea. I think Jeff has done a lot of research. You've actually published a paper that talks about living in Venus and why you may want to do it. I think some of the key motivations would be doing telerobotic exploration on the surface of Venus. The other aspects that are nice about floating in the Venus atmosphere is that you're at the same pressure. If you're at the right altitude, you get the same pressure as Earth, which means that if you got a leak in your habitat, just sort of mix at standard rates. You wouldn't get a sudden jetting of air out or anything like that, so you could take your time in patching it. You wouldn't require pressurized suits either. But you would need protection from the sulfuric acid, and you'd probably need some type of breathing mask, as the CO2 and other items in the Venus atmosphere would instantly kill you if you breathed it. So, and if you can get over the fact that if whatever is holding you up, probably helium or hydrogen in your balloons, if that leaks and you start falling to the surface or you fall over the railing, you're instantly going to burn to your death.
But the sunsets would be incredible.
Yes, absolutely. No, I think if you were going to sell it as far as a tourist place, going to Venus to see the sunsets would be incredible. So I don't know, Jeff, do you have anything else to add from your?
Well, you've added a lot of my bullet points, but the atmosphere, we talk about how hostile the surface of Venus is, but you get up a little bit and it becomes quite nice. If you get about 53, 55 kilometers above the surface, it is the most Earth-like environment in the solar system other than the Earth. So there you go, float at 53, 55 kilometers above the surface.
Is it easier to get to Venus than to get to the surface of Mars?
They're actually pretty similar. Venus has a little bit more of a gravity well, so there's a little bit more stopping that you have to do once you get there.
You don't have to go as far, right? So you don't have to have a full EDL solution. You can just kind of...
It's a little closer. It's a little faster to get there. So when you go down, you go faster than when you go uphill.
But remember, you have a new challenge. You're no longer EDL, you're entry, descent, and inflating.
EDL.
EDI. So,
right.
yeah, so you have to figure out how to inflate something before you go too deep into the Venus atmosphere that you start burning up and you can pop back up.
EDF, entry, descent, float. It's been done, actually. The Russians put balloons into the atmosphere of Venus.
Yep.
So entry, descent, float is a
ITRL.
unknown technology.
Well, for those of you on live stream who couldn't see the vote, Jonathan and Mason won for the extreme environments. But Jonathan's been, I think, convincing us that Venus is still pretty treacherous. So maybe that vote will change. So onto Icy Moons. I know like people have talked about there's an urgency maybe to get to some of these Icy Moons. We don't know how long some of them may have habitable or potential water. Liquid water on them still. How do these Icy Moons evolve? Is there anything that is urgent to you as maybe a prime target in your opinion?
Well, that's one thing that we'd really like to know. One reason that we want to go out there is to understand how these icy moons evolve, what their history has been, because they haven't always been the way that they are. What we are, however, beginning to understand is that many, probably most of the icy moons get warmer as you go further down and have oceans underneath the ice. Several of the icy moons of Jupiter, of course, have not just Europa, the one everybody talks about, but Callisto and Ganymede also look like they have liquid water underneath the crust. Enceladus, everybody's been talking about, not only does it have liquid water, but it sprays that liquid water out into space. Titan as well. I was talking about just the outer shell of Titan having hydrocarbon oceans, but once you go below that, you get to layers of clathrates, and below that, you get to almost undoubtedly a liquid water interior. I say actually liquid water, but that's probably should be thought about, because what we know about Titan is that it certainly has a lot of water. We know it has a lot of hydrocarbons, but when you talk about the compounds that are sort of between hydrocarbons and water, you'd be talking about alcohols. So my thinking is that the interior ocean of Titan probably isn't water per se. I think it's vodka. I haven't published that yet. I'm thinking Icarus, maybe nature.
That could be a more promising destination than Proxima B, Mason. Do we have questions from the audience here? We have a lot of live stream questions that I'll get to as well. There's one back there, yes.
Could we possibly make some sort of genetically engineered microbe that we can inject into Venus's atmosphere? Could we bioengineer a microbe that can use the sulfuric acid and convert, or some of the CO2, some of the volatiles in Venus's atmosphere to convert it and potentially stop the runaway greenhouse effect?
That's something that Carl Sagan proposed in his very first paper elucidating the greenhouse effect on Venus back in the very early 1960s. He said, well, we now know, or he sort of proved that there's a very high greenhouse effect, and he said, well, if we could put microbes, photosynthetic microbes into the atmosphere, it would be able to convert the carbon dioxide to oxygen and perhaps reduce the greenhouse effect. It turns out he was wrong. And eventually, Ethan, he admitted that he was wrong. At the time, they didn't understand quite how thick the atmosphere of Venus is. If you converted the 92 bar of carbon dioxide atmosphere entirely into carbon and oxygen, you'd be left with 60 bar of pure oxygen. And 60 bar of pure oxygen would make anything burst into flames when it touched the surface. So most notably, all of the carbon that you had so carefully fixed to convert the carbon dioxide into oxygen would immediately convert back into carbon dioxide. It wouldn't be stable. That's not to say that a lot of people haven't looked at possibilities of other means of terraforming Venus. It's a tough problem. Part of the problem would be converting some or all of the atmosphere into oxygen. But that's only the easy part of the problem. Reducing the temperature is the hard part of the problem.
To give NIAC a little bit additional credit, I think it was 2004, there was a NIAC study by Amy Grunden and a collaborator, she's from NC State. They looked at using extremophiles and manipulating the DNA somehow to make them suitable for growing on the surface of Mars or other extreme environments. So it's not too much of a stretch to think that we actually have a lot of the genetic shall we say, code that we might need to develop an organism that could survive on another planet, and if it survived, could achieve some other goals. It could be something like terraforming, maybe more near term. It could be fixing nitrogen. It could be actually providing food in some other way. Maybe a small modification of existing crops could help them grow in an environment as hostile as Mars. So NIAC has, in fact, taken a look at some aspect of that already.
Any more questions in the room? Okay, well, Jonathan had the top live stream question before. Now I'm going to combine these two for Mason. How will we know if our microsat made it to Proxima b, and are there ethical implications of sending a projectile at point 2C at a planet which may have life?
So as for the first one, it's a difficult technical challenge, and I have a few slides up here, but we're going to do that later, right?
Yeah.
Okay, so just briefly, clearly you need to send some data back. I would say there's still potentially some value, maybe it's more spiritual than technical, in sending something out there and having the belief that maybe it reached its destination. This would be like the golden record on Voyager, for example. We don't know where that will end up unless you watch the first Star Trek movie. But assuming that it just kind of goes off and represents some kind of dissemination of human intelligence or presence into space, I suppose there's some value there. But realistically, we'd like to get data back, right? How can we do that? The Breakthrough Starshot folks at least have a couple different ideas. It looks like optical communications is probably the best approach. You still need a huge receiver back on Earth, but using the calculations that Phil Lubin and others have been working on and have written papers about, it looks like whatever the optical system was that generated enough power to send that sail toward Alpha Centauri might be large enough to capture enough photons to get data back from Alpha Centauri as well. And that's even if you had a laser shooting only 1 watt, let's say, from the area around Proxima b. So it seems at least feasible by a means we understand today. I would still call that something like TRL-1, though. That's the first part of the question. Second part, ethically, I suppose I do care about ethics. I can't say that I study that professionally, but my opinion, for what it's worth, is that I think we would be less concerned about the risk to any, let's say, potential life on that planet, given that this thing is going as fast as it's going to go, almost certainly will ablate and disappear, turn to a plasma, as soon as it hits an atmosphere. There's probably other statistical games you could play about what are the odds of this thing actually striking anything important on the surface. But I would agree that there's a non-zero risk to some life at another location. You could argue there's also issues of planetary protection, right? What right do we have to send this thing to some other planet when we might, who knows what, infect them in some way? It's a fair question. I also think that the risk of that is extremely low, simply because the environment that this will be in, all the ultraviolet radiation near Earth and maybe near Proxima, and the temperatures, the extreme temperatures it receives, will almost certainly kill off anything. And let's not forget, again, the sudden demise this will feel if it ever comes close to the planet. You know, something traveling that fast clearly will burn up in the atmosphere. I wouldn't even call it burning up. I'll just call it vanishing in a puff of electrons and neutrons and things. So I think not to be concerned at that level. But there's definitely an ethical question here to be answered.
Thank you. Another live stream question. Oh, actually, here's one right here.
So a little bit of a follow-up to that question. You said that interstellar, you're going to be occasionally striking ions. As you get inside an atmosphere, inside, say, the orbit of, I don't know, well, inside, say, 50 astronomical units, doesn't the medium start to increase, and would you vaporize long before you got to, like, our entry interface of Earth?
I'm afraid I didn't catch all that, but you're asking...
Okay. Yeah, well, would you end up vaporizing just because you're in the near solar medium rather than waiting to get to the traditional dense atmosphere like we have in Earth or Venus?
So it's a great point. So the interstellar medium, again, if I understood the question, is much more rarefied than anything we're going to see near Earth. And remember, if this particular idea works well, it will have accelerated to 0.2c soon after it leaves a low Earth orbit or wherever it starts from. So it's going to be encountering probably the most danger in the solar system and then in whatever destination solar or star system it reaches. So I think that's clearly where the risk will exist. I agree. I wonder if that's even detectable. It might be that some early phase experiments, some early flight experiments might tell us what are the statistics of this thing surviving, because if it's damaged by a collision, it'll be a dramatic collision. One thing to think about is what's the signature of a collision like that? Well, remember, you're going 0.2c, right? So all these particles that strike the surface, if they slow down appreciably, and presumably they would, suddenly break. That is, they suddenly slow down. And if you recall from some particle physics you might have seen somewhere, there's this thing called Brimstrolling Radiation. It's breaking radiation. So as that sail strikes those particles, and those particles slow down, they emit maybe X-rays or ultraviolet rays or something. So it could be that a signature, a visible signature, or at least detectable signature of something slowing down due to impacts, could be that it's emitting ultraviolet or X-rays. Of course, it's a little subtle because that frequency will have been blue shifted, but whatever, you see my point. Maybe you can actually see that happen. So it might be possible to conduct a series of flight experiments to verify exactly how bad that would be. But you could be right, that could be the showstopper.
And I'll just do one more question from live stream, and then we'll continue with the presentations. This could be Jonathan here. It's our top question. Is an underground mission to Venus viable, and how deep would a rover need to drill in order to reach a survivable temperature?
So that's an interesting question. I don't think you're really going to do an underground mission that's going to get to survivable temperatures at any point in time. It's not something that we specifically investigated, though. You're better off looking at probably a balloon mission, which stays higher in the atmosphere, or an aircraft mission of some type, if you want to try and do something with current temperature or technologies that work at current temperatures. But yeah, I don't think you're going to get really any advantage going underground, because Venus as itself, it's just sort of, from what I understand, radiating its heat outward. And correct me if I'm wrong on that, but.
No, yeah, that's true. There's no reason to think Venus gets cooler as you go down. On the Earth, some places it gets cooler as you go down because the subsurface is at the average temperature of the climate where you're at. So if it's summer in, say, the Mojave Desert, you can go down and you get the winter temperature, or at least the average temperature. But on Venus, unfortunately, the low temperature is the same as the high temperature, and it's still pretty high. So it does not cool down as you dig under the surface. You get only, it only gets worse.
Right. The other potential area where you could go that's slightly lower temperature is if you could land on the top of a mountaintop. And there, I mean, you're still talking, 400, maybe 300 degrees, high 300s.
With the top of the highest mountain on Venus, Maxwell Montes, with the adiabatic lapse rate, it's about 390 C. Mm-hmm. So that's a whole 60 degrees C lower than the average temperature. That's every little bit helps.
Yeah. But still well above most traditional electronics, for sure.
Okay, we're going to move on to talking about enabling technologies, what NIAC is about. the core of what NIAC is about. We're going to start back with Mason on going interstellar, I think.
So this will be a lot shorter than before, since we already talked about technology quite a bit here. So I'll try to keep this brief. It's a kind of coupled technology development challenge here. In this particular case, where we're not using a large fusion-powered rocket, or we're not doing something that involves physics we don't understand, like maybe the EM drive or some wormhole thing, something that we think we could build. The challenge is, could you make something small enough that also survives? As I said earlier, maybe you want to spread out these electronics so that no single transistor gets killed by an impact. That might be the way to go. I suppose, again, shielding is an option, but it's a lot of weight. And for this particular design, that's our kind of test case to thinking about this problem, we're talking about a 1-gram spacecraft. Okay, so 1 gram spread out over about 4 meters. That's a hard challenge from a materials science perspective. So it's coupled. You got the problem of making electronics that will work and make sense over the course of 21 years with extreme thermal swings. They need to survive the very hot environment of that laser striking the sail, the very cold environment of the interstellar medium, and even though there is not much thermal cycling, it does happen 2 or 3 times during the mission that these temperatures change significantly. So there's a material science challenge, there's a sort of electronics functionality challenge, and there's the challenge of making something thin and yet structurally sound. I've tried now with several graduate students to model an extremely thin spinning sail of the type and shape we would want, and I cannot find a commercial piece of software that'll do it for us. Anyone out there who wants to sell me their software, please let me know, because I have not yet found anything that can come close to modeling the structural dynamics of this body. So there's probably also a modeling challenge, and despite that NIAC might not fund modeling capabilities, we need that for this kind of thing. So that's one of the technology challenges here, is this coupling among all the different subsystems. When I was a little baby engineer, I worked in Texas here on tilt rotors, and you've heard of the V-22 and other things. That was an exciting and wonderful job I had. I also learned from the program manager there, John McGee, that you limit yourself to 1 miracle per program. As I said before, we got several here, and maybe worse, they're coupled together. So it's particularly thorny as a technology development issue. So we did build this prototype here, and I'm not trying to toot our own horn, just kind of give you an example of what we can do. We know we can build multifunctional devices on silicon. Each one of these roughly centimeter squared objects includes regions on it, some of which are in fact the devices you would put into Breakthrough Starshot. Others are just kind of placeholders for things we would need to have but we don't have yet. Here's a zoomed in version of this. This is actually the mask that we use to build these things. Of particular note, of course, you got the we've got the processor, you have memory, the things that you would expect. Little cameras, these are based on a device called the Nani, and they were kind enough to give us some specifics. So we think we could probably assemble a system that consists of those components. A little harder will be what folks in the program called photon thrusters. I call them LEDs. That's what they are. They spit out photons and they emit light, and they're diodes and LEDs. An expensive version of an LED is right here. This is a 1-watt laser, also an LED, basically. You can build these things. The challenge is, can you build them all on a single platform? Well, I think those are challenges we can address. We know that we can make a path from here to there. So a single system on chip that would do this trick is probably not that far in the future. But it doesn't necessarily have the rest of those features we want. Again, temperature survivability, long-term operations, radiation hardness, and so on. So these are some of the challenges that you'd encounter. I'll just show you what some of this stuff looks like just for your interest. The processor, the laser diode. We did, in fact, build this in as close as we could to how you would, in fact, make this, and to convince ourselves that it could work. But there are plenty of open problems. As I mentioned, during the laser acceleration coast and near Proxima, there's questions of navigation. How do you navigate relativistically, and how do you navigate this extremely floppy sail? It seems clear that you need to impart stiffness to something that's maybe less than a micron thick. About the only way to do that I am aware of, it's not through adding substrate, because that adds mass. Instead, you're probably going to spin it. So the centripetal acceleration would stiffen it in the way that you can inflate things. It's a similar kind of effect. You can stiffen a thin membrane, but unless you have, let's say, a sphere, which could be a good idea here, the flat thing can probably only be stiffened with a spin. But again, this is one of several different options. Fortunately, there's some much smarter people than I am on board here. You recognize this fella. There's others, too, who are particularly good at solving thorny science and technology problems. So I think maybe the team is up to the task. Communications, we touched on this a second ago. Personally, it's my own belief that a few bits from a distant star system is extremely valuable. I might be willing to live with a few bits. Maybe what you do is you encode a simple answer to a complicated question on board this chip. The question could be something like, do you see several signatures of Earth-like chemistry on this planet? And the answer could be 1 bit. Maybe a few bits for the sake of forward error correction. But still, maybe you can get away with a very Spartan answer to a sophisticated question, as long as we know what that question really is. And if that's true, the job might come down to sending a few bits. Of course, as you send those few bits, you're sending them from a spacecraft that is traveling so fast that if you were able to take pictures or even do spectroscopy, you're doing so over the course of a very short period of time. It's on the order of seconds that this thing has to take a picture or do other kind of science related to the planet as it very quickly zips by and then is gone forever. There really is no practical way of slowing down. I doubt that anybody on Proxima B has built exactly the right kind of laser system to slow down our spacecraft, so we're out of luck there. And the solar pressure, in case you were wondering, is not enough to slow it down appreciably before it would impact that sun or just go on by. So it's a one-way trip. So a few bits from Proxima, I think that's actually doable. And there's some folks, again, Zach Manchester, who's figured this out. He thinks that could be done. It meets all the requirements you would want for communications. Not easy, but it seems like it could be done. Photos, I don't know about that. That's asking a lot. Nevertheless, we got 20 years, so maybe. The other thorny problem here for this particular architecture and for others like it is the cost of the lasers involved. So you can conceive of a system technically that would include the hundreds or thousands of individual lasers. It'll produce 50 gigawatts of continuous power. You could conceive of it, right? But the cost of that is a whole other story. It might cost tens of trillions of dollars in today's money to build such a thing. So clearly that's not going to happen today. One of the main reasons for putting a roughly 20-year time frame on the development of the technology could be that we're waiting for a Moore's law of lasers to kick in. And this seems to be true, at least over the last decade or two. The halving time for the price of lasers has been about 18 months or so. We think that if that continues and we can extrapolate far enough, it'll be on the scale of billions by the time we want to launch this thing. Billions is a lot of money, but it's still within the realm of possibility. But that, again, it's asking a lot, right? So start to stack these miracles on top of each other, and maybe it's not as feasible as you thought. And still, this is probably one of the best bets. It's one of the things that makes interstellar technology so very difficult. The thing that I like about the Breakthrough Starshot concept is it's based on known physics, known technologies. There are no huge gaps along the lines of, we don't even know how to make this device. We can maybe make it now, it's just too heavy. Or we can make it now and it's too expensive. These are tractable problems, I think. The kind of problem, at least, that has been solved over the years. It's different from asking, how can we devise a type of propulsion system no one's ever seen before? That's not a problem that I know how to answer. I think we, or as a team, the folks on Breakthrough Starshot, we think you can answer these other questions. We'll see what it takes. So I want to stop there, though. That's kind of all I have to offer about these particular technologies. I am not the guy to ask about how to develop warp drive. I would like to see it happen. I don't know how the EM drive works. I'd like to know someday. If you can figure those things out, if you can devise a new means of propulsion, this entire discussion changes. But also, if you had something like that, how we do aerospace generally would completely change. So this is probably a kind of irrelevant application compared to the transformative nature of developing propulsion that could actually take us to another star. It might not be going to another star that would be the priority for all of us. If you've got that technology, think of all the other things you could do with it. And to end my comments here, I will say that's also the nature of why we invest in space technology generally. We invest, yes, to go to the moon and to go to Mars and do these things. It's important to do. But we also get a multiplicative effect on our investment. Historically, it's been something like a factor of 2 to 7 return on investment that we make in space in this country. Thank goodness we've done it. I hope we continue to do it. And NIAC is part of making that happen. Thanks.
All right, so long-duration rovers on the surface of Venus. How do we do that? What type of technologies could we use to accomplish that? Well, there's actually two existing well-published concepts out there, both headed at Glenn Research Center that Jeff has actually been involved in as well. And one is an RTG-powered Stirling engine, which cools a set of electronics in the center of this area, and you with a piston Stirling engine, and you keep those electronics at a lower temperature than the rest of the Venus atmosphere. But this is still very much a technology development with a lot of R&D money that still needs to go into it. And it is a relatively complex and challenging system to build as well. Now, there's another area that is very promising as well, which is silicon carbide and gallium nitride electronics. These are electrical transistors that operate fine at 450 to 500, 600 degrees Celsius. And this right here would enable definitely a long-duration lander on the surface of Venus. The main challenge with these electronics, though, is that right now they're at a very low level of development, only making very basic circuits. The largest integrated circuit that's been built with these is somewhere on the order to several hundred to a couple thousand transistors. To give you an idea in comparison, the Mars Curiosity rover, its processor has 10.4 million transistors in it, and your iPhone 7 has about 3.3 billion. So there's still a couple orders of magnitude for that technology to develop before you can enable a rover with high temperature electronics. So that's where we sort of started coming and looking for another concept. And being a mechanical engineer, we found it, of course, in mechanisms. But what's really exciting about this concept, though, is it's not entirely a new concept. It's a new concept for space and space exploration, but it's actually been around for quite a while. In fact, 2,000 years. The ancient Greeks developed the Anti-Thera Mechanism around 150 BC. This was a mechanical computer that would accurately predict the position of the sun, the moon, and possibly even the planets. And it was just a series of gears that would be cranked to determine where that was at. Later on, in the 1600s, automatons really started to bloom in their development. This is an example of the Rider. This is a fully mechanical robot developed by Jacques Droz, a Swiss clockmaker. And not only does the hand move the pen to write letters, you can see how the eyes follow exactly where the pen is at. This is all controlled by a series of cams in the back of this mechanical robot to carry out these interactions. And what's really cool about this device is that what determines what letters it writes are these keys right here at the bottom, which selects which cams get selected. And these keys can be pulled out and rearranged in any order such that it can write any combination of words or letters. So it's a mechanical automaton that can be reprogrammed. An automaton is basically a mechanical robot in a lot of ways. Now, we've lost those for a while, but they've been re-inspired by Theo Janssen, a Dutch physicist and artist, with his Strandbeest. These are amazing creatures that roam the beaches of the Netherlands that he's built, and they even have simple nerve sensing systems in them, so if they start walking into the water, they'll realize they're going into danger, turn around, and head the other direction. So this really inspired us to think, I think with something mechanical, we could build something that's maybe simpler mechanically that interacts with its environment around it, an automaton that interacts with the environment, knowing when there's danger, where to go, and being able to rove across the environment of Venus. And hence the Automaton rover for extreme environments. A wind-powered mechanical rover. And when we were first going into this concept and proposing and working on the concept last May is when we started on this concept. We were going for an all-mechanical rover, no electronics whatsoever. That's changed a little bit, and I'll discuss that near the end in our sort of lessons learned from this. I should note this is a NIAC study. There's several other individuals at JPL who are helping me out on this. Evan Hilgeman, Michael Johnson, Bernard Beanstalk, and Aaron Parness. Like everything done that is a challenging problem, there's a great team behind you to get the work done. And our idea was to make a rover that's fully mechanical, and as long as we design for the coefficient of thermal expansion, we should be able to design a mechanism that can reliably work for months, if not years, on the surface of Venus, powered by the wind, roving around, taking samples, and investigating things on the surface of Venus. So I thought I'd talk a little bit about the various technologies and trades that we're looking at to implement this concept in each of the areas. So first off, we've got the mechanical computer. And actually, mechanical computing reached its zenith in the 1940s and 50s with fire control computers for battleships to determine where the shells would land. And also in Norden bomb sites was another place where they were actually used. But the Soviets have actually been flying navigational mechanical computers as an aid up until 2002, from the very first human spaceflight up to 2002. And I just wanted to show a couple different mechanical computing mechanisms that you can use to sort of build up your mechanical computer. This is an example of a differential adder. You can see that you have inputs on the shaft. You add shaft X1 and shaft X2 together, and then you get an additive output here at X3, which is the combination of what your inputs are for shaft 1 and shaft 2. This is a mechanical multiplier. You can see if you multiply A and B, the linkage drives this output linkage to a new position, which multiplies the two, so you get a total output of 6. You multiply 2 times 3. And then this right here is a integrator, which looks at time-dependent behavior. And so you can see that you have time spinning in this axis here. As you move this backwards and forwards, that can control what type of function you're inputting into your device, changing the overall rate change of the output. So we can do a lot of the basic math and functional analysis that we would need to do with these analog mechanisms. Further, there's a number of digital mechanisms we can use actually for this mechanical computing as well, creating equivalents of modern computer logic gates. We can do a purely mechanical OR gate, which you can see here, where if either of pin A or B is true, you end up with a true output. You can do the same thing pneumatically. I should mention there's equivalent solutions for NOR, NAND, and all the rest of your basic computing logic gates that you can build these mechanical equivalents to them. And a really interesting piece of work is someone who actually took a bunch of these components together and built an 8-bit processor by Emory and M. Burns at the University of Michigan. That was a really interesting piece of work. So one of the questions, though, once we look at and see, okay, we can process data on the rover using this mechanical computer, how do you get the data off the rover? And that's a big question that a lot of people often ask. If you would have read our original proposal, our first idea was to use phonograph-style records made of a metal that would be soft on Venus, inscribe it with various indentations, put them into balloons, launch them into the high atmosphere of Venus, where it's a nice 20 to 30 degrees Celsius, and then pick it up with a solar-powered drone. But of course, as we started to look into it, it's a little bit too much of a Rube Goldberg, probably even for NIAC. So we decided we had to find something that was a little bit more robust as we entered into our phase 1 study. And one of the most compelling ideas for a mechanical signaling system would be to use radar targets. Now, often you see these on sailboats, and what they do is they create a very large radar reflection, such that a small sailboat appears very large to a container ship or a cruise ship with these corner cubes right here. And now, instead of just getting a bright spot on those corner cubes, though, what we'd do is we'd put a shutter over that corner cube there to be able to modulate the signal and then be able to send data from the surface of Venus to an orbiter overhead with a radar. Finally, we were looking at also possibly using spark gap or vacuum tube transmitters, because it turns out early radio devices work well at high temperatures. The only challenge is that you have to hold a vacuum, which is a really hard problem when you have 90 bars surrounding you. That's a large challenge there. So then as far as the power and mobility system, now that we've talked about how we get the data off the rover, we're looking at a wind-powered rover using a wind turbine to generate our energy. And anybody who knows a lot about Venus knows that the wind only is about 0.3 to 1 meter per second. And that's much slower than what most wind turbines on Earth operate at. However, you have 90 times the density, So you're actually able to get a decent amount of power, or I should say a low amount of power. So you're running a low power rover, but you can still get enough power from such a wind turbine to do roving and do some basic science on the surface of Venus. We take that wind energy and store it. We've been looking at springs, storing it in compressed gas, or what looks like the most practical option right now as far as being most efficient mass-wise is storing it within a flywheel. And then, of course, we have a mobility system which allows us to move around the surface of Venus. And as you saw in the animation, one of the first ideas we had was these walking leg devices, partially because we could keep the rotating member inside the rover and then just have compliant mechanisms on the outside of the rover, so we didn't have to have any rotating joints that dust could potentially clog up on the external surfaces of the rover, and partially because they're awesome. So we had an A-team study, an architecture team study at JPL, and we actually invited Theo Jansen, the creator of the strand piece, to join us in that architecture study, and he was nice enough to come. And one of the first pieces of feedback he gave us is, those legs work great on the smooth beaches of the Netherlands, but if you're going into an uncertain environment, you're looking for a sure disaster. So we've been looking at more traditional ways of locomotion, wheels or tracks, or Theo actually suggested another concept that is really intriguing, which is a caterpillar crawling mechanism. And what's really cool about this mechanism is that it only requires a rotation of roughly 20 degrees between each linkage. So that's something that you could very easily do with a compliant mechanism, and you wouldn't need to have any rotating parts on it, which could help us survive on the surface of Venus for a longer period of time. So I've presented sort of a lot of ideas and sort of where we're starting to head a little bit, but I wanted to sort of summarize with what we've learned in the phase 1 study of our NIAC up to this point and where are we going from here. And probably one of the biggest things that we've learned is the most practical approach, actually, though, is instead of a fully mechanical rover, is going to be a hybrid rover that combines the best of high-temperature electronics and mechanisms. And the reason for that is, as we were looking at doing mechanical computing, if we're trying to make a direct copy of a regular digitally programmed computer with a mechanical computer, you end up even at the MEM scale of something that's going to be less efficient with regards to power, less efficient with regards to mass, and you're looking at similar integration levels as what you have on the high-temperature electronics. You can't really beat them in that. However, where mechanisms and mechanical and computing-inspired devices really come into play and are really beneficial is using mechanisms in a smart way such that they simplify the overall rover design. So the technical requirements on the electrical systems that are involved in the rover are less than what they would be. So designing a very robust, simple rover that can roam the surface of Venus. So that's where we're moving with this idea, and with the emphasis on developing something that's an instrument-supporting architecture too. Most of the instruments to really get good science data, they're probably going to need to be high-temperature electronic instruments. And actually what's really exciting is a couple of months ago, NASA released a call called Hot Tech, which specifically was a call to develop technologies for electrical technology specifically for operation in high temperatures, such as Venus. So we expect that there'll be a number of instruments being developed out of that call once the announcements are made. But those would be stationary once they got to the surface of Venus. And we would give those the opportunity to roam the surface of Venus, to see different geological units on the surface of Venus, different geological areas, and look at weather cycles, things that you have to be on the surface of Venus for long periods of time to do. And we can also use the mechanisms where we need to fill the gaps in high-temperature electronics. One of the uncertainties right now is a high-temperature transmitter. To my knowledge, that has not been fully developed and demonstrated yet. So we may need to be using a retroreflector with a shutter on it to communicate the data back to an orbiter. So it's exciting to think about a rover that is robust, mechanical, roving the surface of Venus for months at a time, allowing us to get new data that we maybe wouldn't be able to get in any other way. And that data can help inform us then of what made Venus the way it is, why is it such a hostile environment, and then when we look at those exoplanets, how do we know that it's an Earth and not a Venus? So I'd like to give a special thanks to a number of individuals who contributed on this work beyond the co-authors. one of the fun things about an idea like this and a NIAC-funded idea is everybody's always excited to share their ideas on how to implement something, or always interested in what makes it work and how they can assist with it. So it's been an extremely fun project to work on up to this point, and we hope to get a lander on the surface of Venus sometime in the next couple decades. So, thanks.
Moving from hot to cold. Well, let's go out. So here's, I have to, I suppose, give a little bit of a shout out to my buddies at NASA Glenn. We've been lucky to work on a number of different concepts for exploration with NIAC. And if you want a concept for how to use the wind on Venus, here you go in the lower right. That's our Venus concept. We think we should sail on the planet Venus. But let's go a little bit further out into the solar system. Let's talk about how we can explore Triton. I told you why Triton's hard. It's far away. It's very cold. But nevertheless, we're working on how can we explore it. What we would like to do is not just land at one point on Triton and wheel around maybe for hundreds of meters, maybe as far as the Mars Exploration Rover has gone 26 miles. We want to fly. We want to fly around on Triton. So what we want to do is make a vehicle that can land on Triton, have long-range mobility, can fly around on Triton, and of course communicate back to the Earth. So our top-level trade study, how are we going to fly around on Triton? Well, we need to refuel, and we need to have an engine that's capable of being refueled on Triton. So we have a radioisotope rocket engine. Some of you may have seen my paper this morning on some of the analysis of radioisotope rocket engines for Triton. We store thermal energy, deliver it to the propellant, and then we acquire propellant at Triton. Let's look at some of these problems. Well, how do we get there? It's tough. It's a long way away. We looked at chemical capture. We looked at solar electric propulsion with chemical engines. We looked at nuclear electric propulsion, but we settled in on using a solar electric propulsion system to get there using aerocapture in the Neptune atmosphere to stop once we get there. That's the one advantage that Triton has over Pluto. If you're trying to go to Pluto, stopping at Pluto is really hard. Triton, on the other hand, has this big gas giant planet nearby. It has Neptune. So our thinking is, why not use that? Why don't we use the atmosphere of Neptune to stop us once we get there? So it allows us to get there in a reasonable amount of time and yet have a reasonable delta V for stopping at Triton. So what do we do? How do we get propellant once we get there? Well, there's lots of nitrogen. So we looked at a lot of questions. Well, what if we just pump down that 1 Pascal atmosphere? What if we just compress it? The nice thing about compressing the atmosphere is it's everywhere on the planet. We don't have to worry, well, what if we land on a barren rocky plain that does not have nitrogen snow? An alternative to other things we looked at was just putting a heat source on the surface and subliming away that nitrogen snow, making our own temporarily thick atmosphere, or just mechanically gathering, scraping up the atmosphere, drilling into the snow. But for the baseline study, we said, well, let's see what we can do in the way of just pumping down that atmosphere to gather the nitrogen. Once we've done that with our radioisotope engine, we can hop. We can take the nitrogen we gather from the surface, put it through our engine, hop. Here's a notional hop, a 5-kilometer hop across the surface of Triton. The paper that I was presenting today was looking at engines that are a little bit better than that, engines that could perhaps double the specific impulse and get you quite a bit farther than the 5-kilometer hop. But the 5 kilometers satisfied our baseline science plans, which are we should be able to land at one site, but then move around to other sites, and in fact do some aerial photography from one place to another to look at different sites on the surface of Triton. So there's the hopper, a cold place. So I gave you Amundsen over on the right to give you a little bit of a scale. This is a hopper that's just a little bit bigger than a human being, dominated, of course, by that large propellant tank that gathers up the nitrogen and uses it to fuel the engine. Here's the mass summary. Here's our point design for the initial look at what the vehicle would look like. Comes to about 500 kilograms, about 1,000 pounds. But that, I should mention, when we do our design studies, much experience in the past has shown that a design done by the engineers at the conceptual design never comes in quite as light when you actually make the hardware as the engineers said it would when they did the conceptual design. So one of the features of accurate conceptual designs is you have to account for that. So we call that the growth factor. So we account for a 30% growth at the system level to account for all of the little things that come in just a little bit heavier than what the engineers said. So 500 kilograms, that's not too bad. That's something that we can send to Triton. So here we are. Here's our view of the Triton hopper on the surface of Triton. It would be by far the most distant object ever landed on by a vehicle, with one of the Triton geysers off in the distance. And here we are with the robotic arm pointed out, sort of scraping up some of that cryogenic 33 degree Kelvin soil. Well, what do we do? Well, it's the most accessible object in the Kuiper belt that we can get to. It's an interesting thing. We can perhaps learn a lot about these most numerous examples of solar system objects, of primordial objects that give us something about the early solar system. But let's go, we were talking about Titan a little bit earlier. We said it has lakes. Maybe they're big enough we could even call them small oceans. Well, let's not just sail on the oceans. Let's sail below the oceans. So we want to design a submarine to sail the seas of Titan. Why a submarine? Well, it turns out to be an efficient way of doing in situ science to get right down in those hydrocarbon seas and look at not only what's in the seas, but what's under the seas. So here's a radar image of those seas on Titan. For scale, the largest of those seas is about the size of Lake Superior on the Earth. It's so big that if you stood on one shore, you'll be very cold. But if you stood on one shore, you wouldn't be able to look across it to see the opposite shore. Here's a radar map. So our object was to be able to have a scale of sailing on the sea that could take us all the way across the planet in a nominal 90-day mission. 90 days was picked to be about the same as the nominal mission for the Mars exploration rovers. To do that, to get that 1,800 kilometers, a little bit over 1,000 miles in 70 days with 20 days sitting at one spot, we only need to go about 1/3 of a meter per second. So can't I play that video? Come on, how do I play the video here? Yeah, good. So here's the video of the Titan submarine. have artistic license here. Of course, we don't know what we find. That's why we're going there. An overview. One of the features of the Titan submarine is direct-to-Earth communications. In this design study, we did not rely on an orbital communication satellite. We have the capability to send data directly back to Earth. And that's that large dorsal fin on the back. It's not actually a fin. That's our phased array radio antenna that enables direct-to-Earth communications. Power would be from a radioisotope Stirling electric generator. And here's a little bit of a size to it. Yarr. How do we get in? We said, well, we're coming into an atmosphere anyway, so we stole a design from the X-37 to come into the atmosphere, come down, a lifting body, then do a deep stall maneuver right above the surface and drop the submarine into the surface. So with that said, here's the difference between Earth and Titan submarines. On Earth, we have an ocean that's about a ton per cubic meter. At Titan, it varies between half a ton and about 0.6 tons per cubic meter. It's hydrocarbons, liquid natural gas. Earth is about 0 degrees to 30 degrees C, from freezing to warm water. On Titan, we have minus 178 degrees C, a little bit cold. But the nice thing about Titan is the pressure doesn't increase as much with depth. Every 10 meters, we get 1 bar of pressure on the Earth. But on Titan, we have to go 115 meters down before we get 1 additional bar of pressure. So we can dive pretty deep on Titan. So just sort of looking at that, NIACs are programmed to look at missions beyond the next generation. There's a lot of the solar system out there. We've been exploring Mars in some depth. We've gone to asteroids. We've orbited some other planets. But it's time to get out there and see some of the rest of the solar system. I have to say one more thing. If you like the current generation of the Titan submarine, wow, just wait till you see the next generation of as we've gone into phase 2. This is going to be really cool. So stay tuned for the next generation.
That was an invitation for you guys to come back to next year's SciTech. So yeah, are you guys excited about all these different NIAC concepts? Has it inspired you to maybe submit your own creative ideas for funding? We're going to do some question and answer again, maybe focusing more on the technologies now. I'm going to start off with Mason Peck. His question here for Interstellar. Oh, where did it go? Sorry. It was something more, I kind of lost it here, but the question is, if you're flying by Proxima b super fast, how long do you have to actually collect data? And is it going to be sufficient to do anything interesting?
I think you get a chance for one picture. So, and then maybe you can do some post-processing on that picture, send the result back to Earth. If it takes 6 seconds for this spacecraft to go from Earth to the moon, which is one of these quick reminders of how fast it's going, it's going to zip by the planet in a fraction of a second. So you have hardly any time. And that's going by the planet. You have some time as you come up to the planet, of course. But for you to do anything sophisticated as you approach the planet would require some subtle optics, and you don't really have the means for that either. So in my opinion, although I think a camera would be great, it'd be cool to see an actual picture, I think a spectrometer would make maybe even more sense. You have a different kind of optical behavior that way. So you get maybe one shot, but again, the idea is to send many of these spacecraft. They are small, relatively inexpensive. You can launch one a day. So you get many opportunities not just to make the mission successful, but also potentially to take those pictures or take whatever data you want when you finally get there. And that implies that rather than having a single camera approach or a single spectrometer approach, you could have a heterogeneous swarm of these things, different science done, let's say, every other day or so. And that could also be valuable. One quick thought about taking a picture. Let's say we use a more or less familiar camera that charges up CCD, right? So it kind of, you get charge building up, electrostatic charge building up in these little cells, and you capture that information. As the spacecraft is traveling by or toward the planet, let's say by the planet, at first the planet is blue shifted, that is to say it's coming at you fast, and so you receive information that's sort of skewed toward the higher frequency end of the visible spectrum. As you go by it, if you're actually able to turn that quickly, and maybe you can't, but if you could, you would see it just briefly reach its real true color. And then as it goes away from you, if you're still able to take a picture of it, now it's redshifted by a significant amount. So that really confuses the kind of science you can do. It really confuses the optics. And once again, like so many other aspects of this particular problem, we haven't even come close to the technology that would make this work. No one's thought about making a camera that works in an environment where it can be blue shifted and red shifted within a second. It's a cool problem, right? So we technology nerds love that kind of stuff. But it's just an indication of how many surprises are out there when you approach a difficult problem like interstellar flight.
Great. We're going to move on for a question for Jonathan. You actually posed an interesting idea, and you came into the NIAC Phase 1 with a fully autonomous mechanical rover, and you're kind of indicating that maybe a hybrid system might be the proper approach to go with. Have you considered maybe optomechanical systems, maybe optical systems that may be a little bit better for temperatures, less sensitive to temperatures than just pure electronics?
So we have not actually looked a lot into optomechanical systems. We've sort of did a brief cursory look at it from a communications perspective, but of course there you run into the problem of the thick Venus atmosphere immediately clouding what you can do. There's probably some very interesting ideas on what you can do with instruments for those, I think. The other challenge with that will be the optical sensors on the other end. There are some various photodiodes, I believe, that are in the process of being tested or being built for Venus temperatures. But beyond that, there's not much in this traditional area of optics that'll survive at 450 C.
Awesome. Okay, we're going to move on to Jeff here. A question for Jeff. This has been on our live stream question list for a while. Could we utilize the hydrocarbons on the surface of Titan as a fuel depot for trips to deep space? So it's an ISRU question.
Yeah, could we utilize Titan's fuel supply? Yeah, absolutely. It's actually sort of the opposite of the ISRU that we look at, for example, Mars. For Mars, we've been looking a lot at the idea that you could take the carbon dioxide atmosphere and make oxygen. So that's half of the fuel and oxidizer combination for a rocket. On Titan, of course, we could do exactly the opposite, which would be easy to get the fuel, but a little bit harder to get the oxidizer for a rocket engine. You might be able to get both, though, because as I said, the rocks on Titan are water ice. So we might be able to take the rocks, melt the rocks, get water, electrolyze the water to make oxygen, and then use that in basically a kerosene oxygen rocket engine, just like the ones we use now. It's a good planet for ISRU.
Awesome. Well, thank you. Are there questions here from the live audience? I know you can enter them online as well, but if we have questions here, I'll take them as well. Yes.
This one's for Jonathan, but do we currently have materials that exist that could simultaneously withstand the corrosion on Venus as well as the pressure and the vibration of takeoff and really everything else that Venus has that we have to worry about?
So absolutely yes for the pressure, the temperature, and the vibration. The thing that is a little bit uncertain now is what is the effect of corrosion at Venus on various materials. And there's actually a lot of characterization going on right now at Glenn Research Center in the Gear Chamber, where they have a Venus simulated chamber where they can look at the chemical impact on various metals at Venus. But I'm pretty sure as the data comes out of that, we'll find a selection of materials that work well within the Venus atmosphere.
And would composites possibly be a solution to that problem?
Right, there's composites, we've got ceramics as well that are also, and I'm pretty sure that there will be some metals that work out well as also, so.
Back there?
I heard you mention that on the Triton you could go deeper since the pressure won't build up as you go deeper in the ocean. How deep is like the ocean in Titan, and do you expect to find something different as you go deeper in?
Yes, the radio sounding that we have shows spots of the Titan lakes that are deeper than 100 meters deep. So we know there are some places that are at least that deep. There are some places where the radar sounding didn't find the bottom, that the bottom was too far away to be detectable in the radar signal. So we don't actually know how deep the deepest spots are, but at least 100 meters. Sure, we want to look at all of it. We want to look at the lakes from the very shallow environments, which can be very interesting for terrestrial oceans, all the way down to the deepest parts. If there's differences in what we see, well, we want to find out. That's part of why we want to go there, is see what there is to see.
Any other questions here? Back there again. Thanks, Pamela. She's getting a workout.
Thank you. So my question is, I'm a little bit more familiar with the underwater environment at Europa. I know that some of the big challenges with exploring Europa involve actually getting down to the depths. Looking at the Titan submarine, do you see this sort of design as something that is applicable to eventually exploring the depths of Europa? Or do you think that extending the model to Europa would call for a radically different design?
Yeah, actually, that was one of the reasons that we designed the Titan submarine in the first place, is to sort of try to learn the sort of things that we'd need to learn for extraterrestrial submarines so that we could explore some of the exciting worlds like Europa. Not that Titan isn't also exciting, but it would be sort of an existence proof that we can do such extraterrestrial submarines. As you say, a real challenge of Europa is that before you can even send the submarine, you have to drill through the ice. At the moment, we don't know how thick the ice is, and we're not entirely sure if there's spots on Europa that have cracks that might make it easier to reach the ocean, or if we have to drill through 10 or even 100 kilometers of ice to get to the ocean. Another difficulty with Europa is that the water is probably relatively saline. It's probably a saltwater ocean, which makes it difficult to communicate with radio. So an autonomous submarine would probably have to come back up and find a radio beacon, perhaps with a cable tether that connects to a radio station outside the ice. Whereas on Titan, the hydrocarbons are quite transparent to radio. So we'll probably come to the surface to communicate. But now we're beginning to think we don't have to. We're beginning to think we can communicate even underneath the surface and be in direct contact even when we're exploring the subsurface of the lakes on Titan.
Okay, I'm going to ask a question that's been, and then we'll get to the gentleman back there, that's been rising here on live stream. Mason, you spoke about properly slicing the trajectory to account for magnetic patches. How do you detect and adjust for them?
Yes, that's clearly a problem. As I said before, it makes the most sense from the short-term perspective, simply let the spacecraft coast for 20 years. Because there are virtually no resources between here and there, where are you going to find the power to power any navigation subsystems, some sensors, the computation necessary to figure out how to manipulate the spacecraft and then actually to manipulate it through some electromechanical means? It's asking a lot. So it comes down probably to a power issue. How can you come up with power during the flight? I briefly mentioned that you could possibly use something thermoelectric based on the ISM's impact with the surface. Another possibility would be some kind of isotope battery. There are these things, beta voltaic batteries. They've actually been around for a long time. They've been used to power pacemakers and other medical devices. These are batteries, not in the traditional sense, but rather they're power sources, energy sources, where a small amount of isotope, maybe tritium gas, emits particles, and those particles are gathered up maybe in a semiconductor, and that produces a current. But the power available for these things, even with maybe a centimeter cube, at best, is on the order of a milliwatt. That's not a lot of power, right? So it could be that if you were to incorporate some kind of isotope battery like this, you still need to store the energy somewhere, then burst it through whatever sensor or actuator would be necessary. To do that bursting, you need some form of capacitance. And now, a traditional capacitor is heavy. A question would be, if the sail itself is, let's say, metallic or metallized because it's meant to be reflective, then could its own self-capacitance be used? And then you discharge that energy to the plasma surrounding the spacecraft. Maybe that could all work. It's still asking a lot. I think instead, if we can't know enough about the interstellar magnetic field, we would have to take a few guesses and then sort of manipulate the trajectory each time based on what we seem to think is happening. And that's, again, a long-term prospect. It will take many years before these errors start to become evident, if you could even measure them. So it's a great question. Another possibility might be if you can just prevent the charge from building up on the spacecraft in the first place. Maybe you discharge it, grounding it into the interstellar medium. You don't have to worry about the Lorentz force. So I guess my money is actually on preventing the charge from being a problem in the first place, if you could manage it.
Okay, it's 4 o'clock, but do we have time for this question here?
Last one.
Yeah.
Thanks very much, Alvin, for organizing this session and excellent presentations. So my question is for Dr. Landis. How do you deal with cryogenics and corrosion effects at the same time for the propulsion that you have planning to have to send to Titan?
Sorry, the question was, how do we deal with cryogenics and corrosion at the same time?
And corrosion at the same time, because the life would be quite affected by these two factors, the life of the submarine, within a day or so, I would say.
Well, on the Titan submarine, it turns out we're stealing a lot of data from the liquid natural gas industry. It turns out that there's a lot of knowledge base of liquid ethane and liquid propane under very similar conditions. We're looking at the possibility of basically flying a little drone submarine through a liquid natural gas environment. Corrosion hasn't been that much of a problem usually at low temperature. The corrosion is more of a high temperature problem. So I'm not sure that we've even really given much of a thought to that.
Okay, well, thank you everyone for attending the session. If you have questions, I'll be here for a few minutes, as well as maybe some of the panel members.